questions, tweet your one-liners, tweet your insights, tweet your pictures with hashtag XPO23 so that our friends who are not here can follow along with us. And for y'all in the back, you're welcome to come closer, make this a little cozier as we go into our last 2 sessions. And one last reminder, our member lounge is just here to the right. If you need a drink, need to recharge before we move on. All right, so for our next session here at 4 o'clock, I'm really excited to introduce Kraettli Epperson. He's the CEO of Vigilant Aerospace Systems. This gentleman has a 25-year career as a technology company executive. And as someone who came from tech, kudos to you, sir. He's a member of the FAA's BVLOS Aviation Rulemaking Committee and the ASTM F-38 Committee. So he's got some experience to bring to the stage for us today. He's going to be talking about integration of detect and avoid into UTM to support AAM. And yes, I did know all of those acronyms last week. Welcome to the stage, Kraettli Epperson.
Thank you. There you go. Can you hear me? All right. So I'm Kraettli Epperson, CEO and co-founder of Vigilant Aerospace, and I'm going to be talking about how to integrate detect and avoid systems into UTM as a way to distribute those services and provide them out to the largest number of users and use them as part of a coordinated airspace management system, particularly in support of AAM and UAM. So we're really excited about this topic. There's a lot of advancements and new technologies that we've been able to bring out to support this. So a little bit of background about us really quickly here. So Vigilant Aerospace Systems is the name of the company. Flight Horizon is our product. We're really focused on building automatic detect and avoid systems and airspace management systems. So some of these are on board and some of them are on the ground. Systems based on 2 licensed NASA patents. It's been used in projects with NASA, the FAA, at the UAS test sites throughout the US, and now increasingly by the US Air Force and a variety of civilian programs, particularly for corridor development and drone port development. So we're really excited to see the advancement of these types of technologies here in the US right now. It's a fully integrated multi-sensor system, so that's part of the unique nature of this. And we have, as I said, both ground and onboard systems. And it uses both local sensors, so a local radar, a local ADS-B receiver, and other sensors, and online data. And so I'll be talking a little bit about that and providing some diagrams. So our agenda here is we're going to talk about key elements of safety that are required for AAM. We're going to talk a little bit about the technical requirements that have emerged and that are starting to become very apparent. We're going to talk about the FAA's new UTM CONOP that was just announced, version 2.0, which has some interesting insights, technical requirements and technical standards, which we think are really important for actually enabling this industry. The process that we use to design a safe system we'll talk about very quickly, and then we'll talk about some actual components, and this will really be the heart of what we talk about with an example of implementation that we do in our Flight Horizon system, and then talk about really some of the details of the components, and then what the user interface looks like, the UTM interface, and then some example projects, and then finally we'll hopefully have a couple minutes for questions here. So when we talk about key elements for safety in UAM, we're really talking about an interlocking set of technologies to create multiple layers of safety and coordination. So it really is about having multiple layers of safety, and we really believe, and all of the rules and regulations are clearly indicating that you're going to need multiple interlocking systems to make all of this work. And that's because you have to be able to provide safety at least 3 different levels and in 3 different ways. One of these is strategic. This has to do with your certification choice of where and how you fly and what you fly, the operational procedures and airspace decisions and flight authorizations that allow you to fly. And then finally, the thing that we're especially focused on as a company, because this is one of the more difficult problems to solve, is the tactical, the ability to actually have air traffic surveillance, to know your situational situational awareness and to know what you need to avoid collisions. So this is a diagram from the new FAA UAM concept of operations. This is the 2.0 version. They did one in 2020, and then they've just done this one a few days ago. Pretty interesting. There's a couple of things I want to point out in this diagram. I know there's a lot on this diagram, and it's pretty complicated. But what the FAA is pointing out is a variety of interlocking systems to allow both UAS, AAM vehicles, and all kinds of traditional air traffic to coexist in the airspace together and safely, to coordinate efficiently, and most importantly, to be able to rely on services and rely on automation to scale up and be able to really create an efficient, economical future for aviation in the U.S. So this is really exciting that this is the direction we're heading, and so we're really focused on this right now. So there's some key technical requirements that come in when you begin to look at that diagram and look at the rules and look at the emerging operations. So you have to be able to detect, track, and avoid both cooperative and non-cooperative traffic. Cooperative traffic being traffic with a transponder that's transmitting into an air traffic control system, and non-cooperative traffic that is not, either because it is lower altitude, smaller aircraft, not in a controlled airspace, and it has to be detected another way. We believe that you need to be able to use private sensors, particularly at things like drone ports, vertiports, corridors. Those are going to be crucial for enabling and allowing the use of your facility, particularly for landing and authorizing takeoff, and then coordination of both onboard and ground-based surveillance and sensor systems. So we'll talk a little more about that. Distribution of this shared sensor data, extremely important. There's emerging this idea of a supplemental data service provider, an SDSP. This is a concept inside UTM and inside the UTM CONOP and framework to be able to distribute that data efficiently, so you can subscribe to somebody else's radar. You can subscribe to somebody else's information, and you can build a real business out of that, and it can be shared infrastructure. The same way every airport has lots of shared infrastructure to support lower altitude AAM and UAS flights. Distribution and coordination of data, that's emerging with the UTM and more extensible traffic management XTM model, which allows you to make reservations in the airspace so that you're not doing all tactical deconfliction. You have procedural deconfliction that exists in the airspace, and then low altitude coordination, particularly for drone to drone and drone to aircraft coordination. That's where tactical becomes very important. So there's certain technical standards. I won't spend a lot of time on this. I serve on the ASTM F38 committee and working group. And so there's some great industry standards quickly emerging and maturing to enable this. Those standards are very important because they allow certainty for developers like us, so that we know that if we can meet the standard, we can bring a product to market and have a marketplace for that, and we can meet the technical standard, ultimately leading to compliance with regulation and rules. So the ASTM F3442 is a detect and avoid standard. We've just published version 2.0. There's a version 3.0 in the works. And so that's a great working group that's doing a lot of really important and interesting work, particularly for lower risk, lower altitude UAS that carries over into use in other places maybe eventually. Our TCA, of course, EO365B, is a minimum operational performance for detect and avoid. That's for larger aircraft, and we actually implement an ACAS SXU model to implement and be compliant with that. And then there are standards for ADSB, which we also use, and then there's software verification standards. So all these things can help generate momentum and generate certainty in the industry. So our approach to safety is that we go through this process. I think this might be a little different than what we've seen from others. We take a very holistic view, and we understand that you really have to be able to support all of these different levels of safety. So we start out with determining what your goals are, determining where you're going to fly, what you're going to fly. We identify the risks, so this is very important. It's called out in the rules, called out in the standards. All of the waiver processes support this. You figure out what your operational choices are to minimize your need to mitigate those risks. So you determine if you can fly not over people, for example, is a very common mitigation. So you make a determination that you could fly from point A to point B, but if you do it a little differently, you don't have to fly over people, which reduces your risk. there are other mitigations. Then you determine what mitigations are required based on your remaining risks, and then you test and validate and test and validate. And so that's our approach, so that you can achieve a goal and then incrementally achieve another one and another one. So here is the heart of this presentation. This is our system implementation for Flight Horizon. There's a lot on this. I'm just going to go through some of the pieces here. The orange box in the middle is the core of our software. We're fundamentally a software company, and we develop standards compliant airspace management, detect and avoid. So all of these systems and modules go to supporting that process. So we pull in information from registered aircraft directly from the flight controller, so they can register either through a UTM process, or we have a direct connection to the ground control station, or directly to the flight controller. We pull in radar data, often from a portable radar, although our system is scaled up and you can use it with much larger radars, terminal radars. We pull in ADS-B data locally, and then we also pull in real-time FAA data. So we pull in that subscription, particularly for controlled airspace. That can be very useful. We are building up models to be able to pull in SDSP data, so as those emerge, we'll be able to pull in other people's data and sensors as they make that available. And then we currently pull in remote ID data where that's available, and those are great projects that are going on right now. And then on the UTM side, to do coordination, we'll communicate with a FIM system, so a flight information management system that allows you to share information upward, and then discovery and synchronization server that will allow you to share data across USS companies. So USS down at the bottom here is the unmanned system supplier interface. This is the display for the remote pilot to use, and that is the interface up into the UTM system. So that is how our system currently works. I'm going to show you a little bit more practical information about this being used in the field, some projects it's being used on. But this is the diagram that I use to explain the basics of what it's doing. You'll see there's a photo here of a NASA airspace manager. He's actually using our system to do some supersonic flights in Florida to track the aircraft and track their deconfliction. So here's some implementations of this. This is a ground-based system in addition to the one you just saw with the NASA Airspace Manager. This is with portable radar, portable ADS-B, direct connection to a ground control station, other radios and system, fully independent. This is running on a laptop, so it's portable. That's important for some of our projects. On the right-hand side, you'll see the same system, but it's running against a single-board computer installed on the aircraft, onboard radar, onboard ADS-B-in, onboard telemetry connection, and then it runs with the software on the aircraft. And this actually was part of an FAA project. We flew beyond visual line of sight along the Trans-Alaska Pipeline with a Quasi, one of the federal test sites. So that was really exciting. And it was really the first multi-sensor detect and avoid system of its kind that was flown along the Trans-Alaska Pipeline. So the user interface provides you with this center aircraft. This is your own ship, the white aircraft, and it is surrounded by a well-cleared distance ring. So you've got a cylinder there in yellow, an NMAC, so a near mid-air collision ring in red, and then you've got a detected aircraft that is encountering your aircraft. And so the system is automatically providing this loss of well-clear warning, and it's saying descend, slow down, turn left within 25 seconds. The system is speaking to you. The little green line coming off the white chevron there is an actual instruction in 3D space, so you can see what it wants you to do, and it's also speaking to you, so it actually has an audible warning. Here is the same system running, but with multiple aircraft in the system, so that you can see it providing warnings for an encounter between two different own-ship aircraft that the system has been configured to track and provide warnings for, with another aircraft encountering them, and the system is providing warnings on both of those. So because this is typically hosted in the cloud, we can scale this up rapidly and handle the number of aircraft that your operation might need. It could be dozens to maybe hundreds eventually. So talking a little bit more about the UTM functions that we've integrated. On the left-hand side here is just a screenshot of some of the configuration that you do when you connect this system up to a FIMS server to share this information and to provide your flight information. And then you'll see you've got a reservation in a corridor represented on the right-hand side in the picture there. And then we also have, just kind of to provide a little background here, some of the systems that can be turned on and integrated. You can have multiples of these, so multiple radars, different types of radars, multiple receivers, different types of data sources, including FAA data and other forms of telemetry. All right, so I'm going to talk very briefly about just a few projects, and then I think we'll hopefully have a few minutes for questions here. These are some photos from our flights in Alaska, flying beyond Vigilant site under one of the most advanced waivers in the U.S. that's used by Aquasi, the test site in Alaska. We had multiple radars, and this was sponsored by the FAA. This was a fantastic project, provided a lot of information to us and to all the test partners. There is Zach, who's sitting over here, operating in a very cold weather with one of the larger radars that we were testing for the FAA. And then on a better day, without so much snow, there's a takeoff there with the onboard radar system. We also have been operating for several years in cooperation with Oklahoma State University with small UAS, in which we use multiple sensors and multiple aircraft. We do a lot of active testing this way to create encounters and to watch the system live and carry it through this full detect and avoid process to demonstrate exactly how that works. And that's been very, very successful for us. And then we also have an Air Force project, pilot project that's ongoing. We actually have 3 Air Force projects now. And one of them, which we've announced previously, and I can share, is tracking in the training MQ-9 Reapers out of Holloman Air Force Base. That is a situation where they can run it. They can run it in the cloud. They can pull their data in, and they can see exactly where those aircraft are in relation to other aircraft that are being tracked nearby to their flight. So that's been a great project for us, and that's ongoing. All right, so in summary, we believe that safe AAM is going to require coordination of multiple data sources. I've gone over a lot of those. Some of them are from other third parties, some of them are self-provided, some of them are local, and we want to be able to support all of those to make this work. UTM and associated elements, that's an important term, associated elements. The FAA has put out a memo about how to begin to have a roadmap to certify and use associated elements, so third-party services that are going to support your beyond Vigilant site flight tests and ultimately your flights and cargo deliveries. That's being developed now, so we pay close attention to that. We believe these standards can really create certainty, ensure interoperability, which is extremely important. So the UTM features that I showed you were based on NASA's UTM Concept 2.0 and the FAA's concept. And the ASTM UTM standard. So those are the things that we're using to be sure that our UTM system is interoperable and that the USS interface is interoperable with other UTM systems. So very important. It's like a cell phone network. Everybody has to be able to talk to everybody else for it to be useful. Even if you're on a different system, you have a different cell phone, you're on a different network, you still have to be able to talk to each other. We believe that active detect and avoid really requires consideration of air and ground risk and appropriate sensors and surveillance, and so we built up a system to support that around the major risks and mitigations that have to be included in a system like this. And then finally, we really believe that active detect and avoid is going to require these multiple data sources to be able to do correlation, to improve the baseline safety in a UTM system. Meaning that we think that detect and avoid at a tactical level should be included in UTM, in addition to the coordination that UTM provides as part of its major function. And that's really why we've built the system that we've built. So thank you all very, very much. Hopefully we have a few minutes for questions, about a few minutes for questions, so I'd be happy to take some questions.
I have the microphone, and I will bring it to you when you have a question. I have one. Were you only in Alaska in the summertime?
Some of us were in Alaska during the summertime, and I'll say that was me. And some of us, like Zach over here, got to be in Alaska at multiple times in multiple seasons. So we got to test the tolerances of some of the equipment, in addition to the tolerances of some of the people.
I asked because I actually grew up about 20 miles from UAF, so I was having a little homesickness watching your slides.
Yeah, absolutely.
Any questions? Any other questions?
So we'll be here, and I'll be here afterwards. If you want to come talk to me and get a card, we'd be happy to talk with you.
A round of applause for Kraettli and his other friends who braved the Alaska seasons to bring you this great presentation.